Okay, so we're going to look at factorising quadratics when the coefficient of x squared is not equal to 1. So sometimes we refer to the method as the AC method, and the reason for that could be that we think of a general form of a quadratic as ax squared plus bx plus c, where a, b, and c are what we call the coefficients. And for a quadratic where it just starts with x squared, when we try to factorise it, we normally say two numbers that times to make this and add to make this, and it goes into brackets. The difference with the AC method is that we look for two numbers that times to make a times c, but add to make b. So here's an example. Here we have a is equal to 2, b is equal to 7, c is equal to 5. So AC will be 2 times 5, which is 10, and b is 7. So we said we want two numbers that times to make 10 and add to make 7. So those two numbers, hopefully we can spot are 2 and 5. So what we do now is we rewrite this expression, splitting that middle 7x in terms of those two numbers we found. Okay, so the expression hasn't changed. 2x squared plus 2x plus 5x plus 5 is still 2x squared plus 7x plus 5. I've just rewritten it in terms of those two numbers that I knew were going to be important. And now I kind of look at the expression in two halves, and I say, okay, let's factorise this side as a single bracket. The highest common factor is 2x, and I'm left with x plus 1. I can actually straight away copy the x plus 1 onto this side, and I'll say how many lots of x plus 1 make 5x plus 5? 5 lots. So x plus 1 is a factor of the left-hand side of the expression, and x plus 1 is a factor of the right-hand side of the expression. So it must be a factor of the whole thing. That means that the other part, this sort of residual part, 2x plus 5, must be the other factor. So our final answer is, okay, because 2x lots of x plus 1 equals 2x squared plus 2x, and 5 lots of x plus 1 equals 5x plus 5. So 2x plus 5 lots of x plus 1 must make the whole thing. And there we have it fully factorised, and there we go. Right, another example. AC is 12, and B is 8. So two numbers that times to make 12 and add to make 8. So I rewrite the expression, split the middle, copy the common factor. How many lots of x plus 2 equals 2x plus 4? 2 lots of it. There's my other factor. Okay, and sometimes people say, how do we know what way round to write the 6x and the 2x? And the answer is it doesn't matter. And I'll show you now how that works. If you'd written it as, so essentially you've written these two the other way round, the 6x and the 2x, the expression is still the same and you've still chosen the same two numbers. You've just chosen to write them in the other order. It doesn't matter because if I now split the middle, let's look what happens. Highest common factor here is x, and I get a 3x plus 2. I copy the 3x plus 2 over, and I get 2 lots of that gives me 6x plus 4. So what I find is I just find them the other way round. So I find the 3x plus 2 as the repeated common factor, and the x plus 2 is the residual bit, but ultimately I get the same answer. Okay, so two ways. It doesn't matter what order you do that middle term. Let's have a little look at this one. So this time we've got to be really careful with the minus signs. A is 3, B is 1, B is not x, it's still sort of 1x. So B is 1, and C is minus 4. That minus is attached to the 4. AC is minus 12, B is 1. And this is where it gets trickier when there's negatives. Two numbers that times to make minus 12 but add to make 1. If the product is negative, that means there needs to be one positive number and one minus number, because two negative numbers times to make a positive. So I need one negative and one positive. And I need them to add to make positive 1. So it needs to be more positive than it is negative, so that when I add it, it's positive. So the numbers are going to involve 3 and 4, and the bigger number is going to be positive. So the numbers are 4 and minus 3. They times to make minus 12, but add to make positive 1, because I've picked the bigger one as positive. So let's rewrite this. 3x squared plus 4x minus 3x minus 4. So I've just written the positive 1x as 4x minus 3x, and then I split the middle, and that minus is attached to the 3, and I factorise both bits. So the highest common factor on this side is x, and I get left with 3x plus 4. I copy that across, 3x plus 4. 3x plus 4 times what is minus 3x minus 4 times by minus 1. So my factors are 3x plus 4, x minus 1. Okay, so that was slightly trickier, that one. So again, let's look out for the minus signs. So AC is equal to minus 21, and B is equal to 20. So two numbers that times to make minus 21 but add to make 20 would be 21 and 1 if we make one of them negative. So because we want it positive 20, the bigger one needs to be positive. So the numbers are 21 and minus 1. They times to make minus 21, but add to make positive 20. So let's rewrite it. So 7x squared plus 21x minus 1x minus 3, split the middle, highest common factor, copy across. How many lots of this make this? Minus 1. Okay, let's keep going. So this time, they times to make minus 12 and add to make minus 1. So again, the numbers are 3 and 4, but this time we need the bigger one to be negative so that it adds to make a negative. So the numbers, so the factors were 3 and 4, but the numbers are minus 4 and positive 3, so that it adds to make minus 1. And if you've written your answer as x plus 1, 3x minus 4, the order you write the brackets doesn't matter, but it's crucial that we recognise that they are the two final factors. Okay, so this example, and finally, the other type we need to look at is when they times to make a positive but add to make a negative. So here we need to be careful. 6 times 2. So how can two numbers multiply to make a positive but add to make a negative? The way that that will work is if both numbers are negative, because they're adding to make a negative, so one of them at least has to be negative. But because they times to make a positive, they both have to be negative. And there we go. So we're looking for two numbers that multiply to make AC, but add to make B. And actually the other factorising technique for when x squared's coefficient is 1, and we say times to make C, but add to make B, or times to make the constant, but add to make the coefficient of x, that is still really a subset of the AC method, because A is 1. So AC is still just whatever C is, whatever the constant on the end is. But this technique requires a bit more work. But the steps basically are, we look for two numbers which multiply to make AC and add to make B. We then rewrite the expression in terms of the two numbers that we've just found, splitting the middle B term as the sum of those two numbers. We then factorise the two halves of the 4-term expression, finding a common factor on both sides and a residual factor, which makes the other bracket. Hope that helped. Keep well and speak to you soon.